In the previous section, we handled DMA FIFO underflow and overflow conditions. By the end of this module, you will be able to use a single interleaved DMA FIFO to transfer multiple channels of data. So as we're using DMA FIFOs, one thing to keep in mind is there's a limited number of DMA FIFO channels available. For example, for a 7852 R series board and for a Creo 9074, there are only 3 DMA FIFO channels. So what would you do if you needed to acquire data from, let's say, 4 channels on multiple modules? So if I needed to have 4 DMA FIFO channels, I actually couldn't do that on our on a Creo 9074, right? If I wanted to implement 4 separate DMA FIFO channels for each separate channel. One way I can take advantage of using one DMA FIFO for multiple channels is I can interleave multiple channels of data into a single DMA FIFO, and that way I can conserve my DMA FIFO channels. So how would I do this? So if I have multiple elements of the same data type, then I can put them together in a single array. So if we take a look at that example at the bottom, notice that in module 2, we actually want to get 4 channels worth of data, okay, but we only want to use one DMA FIFO. So in this case, we've taken those 4 channels of data, and because they're the same data type, we can put them into one array. So we built that array, and then the next thing we do is we're going to take that array, send it to a for loop, and then inside that for loop, we're going to iterate through that array, writing one element at a time into the DMA FIFO. Okay, so now let's go to the host side. So now we've written interleaved data on our FPGA, and now on our host side, we want to read it and de-interleave that data. Okay, so let's take a look at our block diagram here. The first thing I want to show here is at the bottom, you have the initial read, and we take a look at the number of elements remaining, and notice that we have samples per channel there, and multiplying it by 4. Okay, so if we want to wait until we're reading, let's say, 10 samples per channel, then that means we need to have 10 times 4, or 40 elements in that FIFO available for reading. Okay, so now we're going to take that, and once that amount of data is available in the FIFO to read, we're going to go into the case structure, and we're going to read those 40 elements. Okay, and then at that point, what we're going to do is we're going to take the data coming out, and we know since it's interleaved as 4 channels worth of data, we're going to decimate that 1D array, and that way we can extract channel 1's data, channel 2, channel 3, and channel 4 from those 40 elements. So on this slide, we're just putting everything together. So we see that the FPGA VI on top, we're going to use the build array, and then we're going to use the for loop to iterate through that array and write those channels one at a time. And then on the host VI, we have to de-interleave that data, and we're going to do that by decimating that 1D array back into our 4 channels worth of data. So in exercise 11.4, what we're going to do is we're going to use a DMA FIFO, and we're going to interleave data on the FPGA VI, and then when we read it on the host, we're going to de-interleave that. So let's take a look at the solution real quick. Okay, here we have the solution to exercise 11.4, and what you would have done is you would have gone to your FPGA VI, and let's take a look at that real quick. And here we see some similar code. So in this case, we're getting accelerometer data. And with this accelerometer data, we want to make sure we transfer all values. So we want to do a buffered transfer from the FPGA to the host. So that's why we were using a DMA FIFO in the first place. And in this case, we want to conserve the number of DMA FIFO channels we use, because we only have 3. So in this case, what we're doing is we are combining accelerometer 0 and 1 in those channels, and we're building an array here, and we're going to iterate through that in the for loop and write those one at a time here. Okay, so this is similar to the code that we just saw on the previous slide. And then if we go to our RT host, let's look at the block diagram here real quick. So here notice that we are doing the samples per channel code that we saw similar to the slide, and if we want 100 samples per channel, for example, we want to multiply that by 2 so we get enough data. So here we're going to compare that here. Once we have 100 samples for 2 channels, we're going to go into this case structure and we're going to read that number of elements, and then we're going to extract that data and we're going to decimate that 1D array to get our original channel data. In this case, the processing that we're doing is we're just building that into an array and changing it to a double precision floating point so we can get that on a graph. Okay, so this graph will show 2 channels worth of data. So real quick, let's just go ahead and run this. Notice that in this case, we are doing a data rate of 51.2 kilosamples per second, and we're also getting 1,000 samples per channel that are going to be displayed here. Okay, so let me go ahead and run this. And I've already compiled my FPGA VI. So this is actually running on the FPGA. And now we're looking at the front panel of our RT VI. So notice that we see that we have buffered data. So this is definitely buffered data. And it looks like things are good to go. We've got 2 channels of data being shown here, and we only used 1 DMA channel to do it because we interleaved the data. You can imagine there could be 4 channels of data on this front panel just as easily if we made a few minor modifications. Now you can use a single interleaved DMA FIFO to transfer multiple channels of data. Next, we will notify the FPGA VI of an event from the host VI using a Boolean flag.